Hey everyone, today I'm going to show you how to solve a Sudoku in a fraction of a second, using programming of course. No way any human could do this. So the agenda for today, we're going to go through the implementation, how to kind of think about this problem and how we can break that down into steps and then implement them. And then once we've looked at the code, we're also going to then have a bit of a discussion on how we can organize the code in a way that allows it to be flexible and extended if we want to in the future. So without further ado, let's jump into the implementation. So whenever I start with a project, I like to think about the components that I need to implement. And having this sort of clear understanding of what you need to implement before you actually jump into the code is a really nice way so that then you can focus on, you know exactly what's happening and you can just focus on getting the work done. So in terms of the implementation, we need to take care of three things. How do we store the grid? How do we see the grid? And how do we solve the grid? Now, how do we store the grid? Basically, how do we tell the program to keep track of things, right? So one option would be a list of lists. And this is in Python. So each row could be represented as a list of length 9. And then we have 9 of those lists representing the whole grid, so from top to bottom. And each number can just be represented as a number in the list, and the blank spaces can be represented as zeros. So that's fine. Another approach would also be to use a numpy array, and that's actually what I ended up using in my implementation. It's pretty much the exact same thing. It's pretty much just a list of lists, except the nice thing about it is it's got some predefined methods that we could use in order to help with our computation and to help extract some summary statistics about that grid, like counting the amount of 1s or 2s in a row, which is pretty handy. Then we have viewing the grid. Well, viewing the grid, we can pretty much use anything. As you saw, we're using a command line, so that's just printing to the command line. That's pretty straightforward. But I mean, in terms of the possibilities, you can also have an interface with an application. You can have it so that it generates images. It's pretty much whatever you want it to be for the grid. And finally, the meat of the question is, how do we solve it? Now, there's multiple different ways to solve it. You can probably discuss in the comments if you really want to. Ways you can solve it. You can use a machine learning model. I'm betting there's also other algorithms that are probably more efficient. But what we'll be using is a backtracking algorithm. So what is a backtracking algorithm? Well, I feel like the best way to explain it is to kind of think about how we, as humans, solve mazes. So, say we have a maze. Well, of course we could, this one's pretty simple, we could just look at it. But if for more complex mazes, we might try going down one route, right? So say we go down the left, that top path over there. So we go down that path, we meet another fork in the road, and we have to choose one of those. So if we choose one of them, we see that we reach a dead end. So then if we choose the other one, we see that we also reach a dead end. So that fork, since we arrived at that fork doesn't lead to any of the solutions. So we have to go back up to the fork before it. And then that way, try the branches off from there. In general, backtracking algorithms can be thought of as a series of choices where we choose one of those choices all the way down. And if we reach a dead end, then we move up one and we try the other possibilities, the other branches. And if none of those branches work, then we go up another, up to the previous fork, up there, and then we rinse and repeat. So this would be a recursive algorithm. So in terms of Python, we'd want to use recursion in order to solve this. Perfect. So I'll show you what it would kind of look like in terms of a Sudoku. Would look at a 4x4 grid because it's just easier than 9x9 in order to visualize what's happening. So we look at the first cell, the first blank cell, and we're like, okay, well, can a 1 go in there? No. Can a 2 go in there? Yep, a 2 can. So we put a 2 in there. Then we look at the next free cell, and we're like, okay, can a 1 go in there? No. 2? No. 3? Yep, 3 can go in there. And then we look at the fourth cell and we realize that none of the numbers can go in there because we have a 4 in that block as well. Okay, so the previous cell then can't be a 3, because if we put a 3 in there, then the next cell doesn't have any possibilities. So can it be a 4? No, can't be a 4 either, because there's already a 4 in that block. Okay, so then we have to go back another number to the previous decision that we made, and we can try another number in there. So if we put a 4 in there, that works. Then by rinsing and repeating that process, we can step forward and recursively step back and try all the possibilities until we reach our final solution. Perfect. I think that's pretty much all the implementation discussion out of the way. Now let's actually jump into the code. Now, in terms of the code, I'm not going to be coding this line by line. I'm merely just going to be highlighting blocks and talking about how they relate to the implementation and giving a more overview approach rather than explaining every single step. But yeah, let's just jump into that. So all the code I'm about to show you is available on the GitHub repository listed below in a file called sudoku.py. And yeah, we'll just go through it. So first off, we need to think about, okay, how are we going to provide the Sudoku grid to the application? So the way I'm doing it at the moment is I have this text file, which is just 9 lines, and the zeros represent empty slots, and the numbers represent pre-populated values. So I have a function here called readGrid, and it reads in the grid, and it interprets the zeros as blanks and the numbers as populated values. So we open the file, and then we read that file, we strip it. So what strip does is it removes white space characters either side, and then we split the lines apart. And then, so we split lines, and that converts it into a list of 9, and then with each row represented as a string. And then we can just iterate through that and convert each cell, each number into an integer type. So this is just a list comprehension to do it. You can also do it with a for loop. So that would be how you do it there. So you're just going through each cell and converting that. And then what we return is a numpy array. So we just convert the content into a numpy array. So that's a list of lists. If you're wanting to do a list of lists implementation, you can just have that. So that's fine. We have now a function which is valid. So what isValid does is it returns whether or not the given Sudoku grid is a valid grid. So in order for a Sudoku grid to be valid, the columns need to have no duplicate values. So no, like there must only be one of each number. The rows must be the same, only one of each number. And the 3 by 3 blocks must also be have unique values in there. So what we can do is using, what we're actually doing is we're checking about a certain point. So say I want to look at the top left corner, like that cell, I'll be checking the row corresponding to that and the column corresponding to that. So that is the point of last move over here. And what we'll do is we will, so this is using numpy indexing, which makes this very easy. If you're to do this with lists, the solution becomes a bit more convoluted. So we extract the row out of the grid. So that would be the row corresponding to the row index. We extract the column out of the grid, which would be the column, which would be, we're looking at all the rows and we're looking at that specific column corresponding to the column index. And then what we want to do is we want to construct a list or an array with the cell block, containing the cell block to be tested. So that, that block of cells, that 3 by 3 block. So what we want is we want to get the index of the top left hand corner of that block of cells. And the way that we're doing that is that if we take modulus 3, we find how far we are away from that corner. So if we take row index modulus 3, we find out our distance towards that corner. So by doing the row index minus that distance, we can actually find the row index of that top left-hand corner. We do the same for the column index, and then we can index the 3x3 grid, and then we flatten it. That just converts it from a 3x3 array to a flat 9x1 array. Perfect. So we have our 3 arrays that we want to test. We can iterate through them, and here we're just counting each of the values and making sure that all the non-zero elements only appear once, right? Zeros can appear multiple times because zeros just correspond to empty values. So that's this for, we're just iterating through and making sure that each of those occurrences is doesn't occur multiple times. And if all our checks pass, then we just return true, as in it is a valid Sudoku table. If any of them fail, it returns false. So that's the implementation of the isValid function. So what we end up having is we've implemented how we store the grid, which is, I guess, how we read and we store the grid, and we've implemented how we check the grid as well. So what this here does is it takes in a grid. This is a rendering function. It takes in a grid and it prints out that rendering in it constructs that rendering and prints it out. So since it's working with strings, it can get a bit hairy, the logic. It's not as neatly packaged together as the other logic. So we have an output list, which is just to help with tracking the formatting. And we have this function here, 3chunk, which basically takes a list and splits it into chunks of 3 elements, where each of those chunks of 3 elements are joined by a delimiter. So, which is helpful for if we want to pass in a row, we can join each, like it's a row of 9, we can change it into a row, a list of length 3, where each element is the 3 numbers stacked next to each other. So if we do that, which is this row over here, we can then join that row with vertical brackets, or vertical bars. And then we can take that then row of 9, those 9 rows, and we can chunk those together in sets of 3 and separate them by just a new line. So that each of them is on a new line. And then we just join them all together with the borders, and the border we specify up here. So that's how the print function works. If we were to go down here, I'm just going to comment out some of it here, so we can actually see it's all working. What we can do is we can read in the grid, and then we can render the grid. And if I run this, we end up with this. So just this rendering. So the main meat of the problem now is how do we actually solve the Sudoku? How do we implement this backtracking algorithm? So with recursion, I find the best way to go about solving it is to first decide what this, I guess, our stopping conditions. So we want to stop for when the, we want to completely stop the algorithm if the Sudoku is completely solved, and we want to move up a level if the cell that we're looking at has no more possible values, right? So those are our return statements. So if the Sudoku is solved, we can return true. And if our particular cell of interest has no more possible values, we can return false. So that's what is implemented down here. But we'll get to that in a little bit. So we'll just ignore this for now, and we'll just look at for our actual guessing process. So for guess in range 1 to 10, what range 1 to 10 will do is it's closed on the left and open on the right. So it will feed us numbers from 1 all the way to 9, and assign guess to those numbers. So it takes the grid, the row and the column, and it makes it equal to our guess. Then what we do is we say, okay, is our grid valid around this row and this column of interest that we've just inserted into? If it is valid, then we move on to the next empty cell. And that process of moving on to the next cell is this recursion call here. So we're just now looking, okay, what about column +1, right? And this is where the function will take over and create another, go through this whole process again before it even moves on to whether it's returning true or not. So it'll go into that instance there. And okay, so we need to think now about our stopping conditions. When do we want to modify the behavior of what's happening? We're adding 1 to the column here, but although we're adding 1 to the column, when do we start wanting to increment the rows? So if our column that we're looking at is above 8, it's off of the board, right? If it's 9, the index 0 to 8, so 9 would be out of range. So then what we want to do is we want to increment the row up 1, and we want to set the column to 0. And if our row is above 8, then we've basically gone along all the way 0 to 9, 0 to 9, 0 to 9, all the way down, and we've reached here, this part at the very end here. So what that will correspond to is a solved Sudoku. So if our row is above 8, then we need to return true. And then this kind of completes the base logic. So if the solved Sudoku, so this is how we iterate up. We check whether the next cell, we go into the next cell, and then we keep iterating through. And if we exhaust all our possibilities and it doesn't return true for all of these, we set that cell of interest back to 0, and we return false. And what this will allow us to do is kind of iterate through this, and it'll return, it'll keep going until it reaches a dead end. It'll return false, which will move back up a recursion level, and it will continue on with the for loop corresponding to that recursion level. An additional check that we need to do is we need to look at the pre-populated values, which is this block over here. And we need to see, okay, we were given originally values that were guaranteed to be true. So these are values that are already in the Sudoku. And we need to make sure that we're not editing those, because at the moment, what we're basically doing is overwriting those if along with the algorithm, because we're only incrementing in the +1. So we want to see if the row column that we're interested in is in the pre-populated rows and columns. And if they are, then we just move on to the next column. And this, where we get pre-populated, isn't exactly clear because I haven't really explained it. It's through this function here. So pre-populated corresponds to record preoccupied cells of the grid. That's what we do straight after we read the grid in. And what this does is it creates a list, and it goes for each row in this grid, for each row index, for each column index, and then that row. So if the grid is non-zero, we just append that to our pre-populated list. And that's just a list of tuples. And that can participate in there. And I think that's pretty much it. What I'll do now is I'll show you kind of the algorithm in action. So as you can see, it's kind of going forward, trying all the guesses, and then backtracking until it can iterate above. And at the moment, I've kind of delayed it so that there's 5 milliseconds between each guess. So about 200 guesses a second. So in terms of the actual implementation, this is all done within 500ths of a second. So, but yeah, this is just a nice overview so you can actually see what's actually happening between each step. And it's done. So that's pretty much it. That's the algorithm completed. We pretty much have a final product that we can just use to solve Sudokus. Now, is that the end of the story? Well, it depends. If you're just wanting to write something to solve Sudokus and you're the only one going to be using it, that's fine, right? The way that we've implemented everything is completely okay. But in terms of, I guess when we code, we want to try avoid coding in a hard way. We want to try avoid hard coding things. We want to be as flexible and as adaptable as possible. Because when the requirements change for your code, it's good to be able to adapt to them easily rather than having to recode everything from scratch. Now, when we look through this implementation, right, we have these functions that are nicely separated. They kind of nicely compartmentalized. So in terms of that, we're good. But I guess if the project changes, right? Say we want to use a different view, right? Say instead of printing out to the command line, we want to print it out to an app or something. Then that will require kind of diving into the script and completely changing how it works. Or in another sense as well, there might be other opportunities to kind of change the functionality of the script in terms of, like, Sudoku isn't the only, you have vanilla Sudoku, which is what we've been solving here, but then you also have additional constraints like knights move Sudoku or different rule sets that you can have on a Sudoku board. So in order to implement those different rule sets, you'll need to dive into this code as well. And switching between rule sets, like say you want an application where you can choose whether you solve normal Sudoku or whether you solve knights move Sudoku or anything like that, have changing between those dynamically, just through the way that we've coded it at the moment, is pretty difficult to do. So rather than kind of take a functional approach, we can really take advantage of object-oriented programming in order to introduce this sense of flexibility to our code. And I'll quickly check out the main branch. I'll also link the branch with kind of the object-oriented approach in the description if you want to follow along. And I'll just show you what we have. So we've defined this object called Sudoku, right? We'll just ignore this up here. We've defined this class called Sudoku, and it has an initialization where it takes in a view. So a view being a view object specified in the views file, which we'll go through separately. So it takes in a view, and it also takes in a path to the Sudoku. And in the initialization, it reads in the Sudoku and does all of that. And records the preoccupied cells. Recording the preoccupied cells is pretty much the exact same as what we did in the previous script, but it stores that in an attribute for the Sudoku. Perfect. We also have a read grid method, so that's fine. We have an isValid method as well, pretty much the same. And then we have a little thing here, before iteration, between iteration, when done, and then we have the solve function. So what before iteration does is it defines a set of actions to do before we even start solving. So maybe this is print out the board for the first time. With between iteration, which we can customize depending on what we want to do. So for the previous, I was showing code how it was dynamically updating as the algorithm progressed. So this is where I was defining that. So between each iteration, I was getting it to print the whole board, and then when done, kind of what we wanted to do when it's done. And this sort of allows us to add more flexibility to our code and what it's doing each step along the way. And then we have the solving algorithm here. And the nice thing about separating it like this is that, say we wanted to implement variants of Sudoku, well, all we have to do is we need to change this isValid function. And instead of having an isValid function, maybe we could have a validator, right? So we have this separate class or set of classes, which are validators. And they basically take in the grid and spit back whether it's true, false, whether it's a valid board or not. And by doing it that way, we can go into a separate file, define all our validators, and dynamically change the validator depending on what we're trying to do. Just like we can do with the view. We can change our view depending on what view we're wanting. In the view file, I have a command view, and this is pretty much the exact same as what we did before, but it's got an initialization method and it's got a render method. And this way, if we change the view, we could just need to change the render method, and then we don't need to change our original code in the Sudoku. So it'll still be view.render, except the view will be different. And that will be defined based on how we initialize the function here. So we're feeding in the command view, so it's going to render based on the command view. So I guess this is a way that you can take your programming up to the next level, this sort of thinking critically about how you structure your code. And also, I guess there is pros and cons, right? If you're just trying to do something, definitely go for the functional implementation. But if you're if you have a reasonable expectation that your requirements will change as you go down the line, giving some more thoughts to how you're organizing your code, how all the pieces are fitting together, it's definitely worth it. So I'd really recommend, especially if you're new to object-oriented programming, kind of looking through the example, GitHub repos linked below with the relevant branch. And yeah, that's pretty much it. I thought I'd just showcase all this to you guys. And I thought it was an interesting problem, and I hope you guys enjoyed too. So yeah.